Continuing our discussion, we will now move on from simple feed-forward neural networks into the building blocks of deep learning for computer vision, which are convolutional neural networks. Before we start that discussion, we'll review the homework or the exercise that we left behind in the last lecture of the previous week. One of the questions there was, how do you backprop across a batch normalization layer? So what you see here is the algorithm of batch normalization that we saw last time. Let's quickly review that in terms of how it looks on this graph, what is known as the computational graph. So you have forward propagation, which is given by, you're given x1 and x2, and given a mini batch of data, you find the mean and variance of x, the inputs out of a particular layer, the activations out of a particular layer, and then you normalize that data using the mean and variance. Once you normalize, you renormalize them by scaling and shifting. Rather, you adopt a variance gamma and a mean beta, which is suitable to solve that problem. This is the main idea of batch normalization, and that's represented by this graph here. The forward prop, as we can see, is quite straightforward, and we just follow this algorithm. The question here is, how do we do the back prop? Let's try to work through the different terms here and understand this. The first term that we have to find out is beta. That's one of the simplest terms to evaluate, so we'll start with that. To recall, let's go back and see what beta was. Note here that in the last line of the algorithm, beta plus gamma times xi hat is the final output yi. Keeping that in mind, so this is the main equation that you may want to keep in mind for the next few slides. So dou L by dou beta, so you can assume that beta is almost an input into y with, so you have this here, gamma times xi hat plus beta times 1 is what is y1. So which means dou L by dou beta is going to be given by dou L by dou y1 into dou y1 by dou beta, and similarly for the other y terms, dou L by dou y2 into dou y2 by dou beta, and so on and so forth. Dou y1 by dou beta, as you can see here, is going to be 1. So this is going to simplify to dou L by dou y1 plus dou L by dou y2, which is the final gradient of dou L, where L is the loss with respect to beta. Let's move on to the next one. Similarly, dou L by dou gamma, remember gamma is the constant that multiplies xi hat. So dou L by dou gamma is equal to dou L by dou y1 into dou y1 by dou gamma, and so on and so forth for all the y terms. And dou y1 by dou gamma, as you can see, is going to be x1 hat by the very definition of these terms. So that term gets replaced by x1 hat. So you have dou L by dou y1 into x1 hat plus dou L by dou y2 into x2 hat, and that gets summarized as a summation in this way. Let's move on to the next term. The next term is dou L by dou x1 hat. x1 is not a parameter, but we need to be able to compute this so as to propagate the gradient to previous parameters in the network. Dou L by dou x1 hat will be dou L by dou y1 into dou y1 by dou x1 hat. Dou y1 by dou x1 hat is given by gamma, as we just saw. That's what we put in here. And similarly, you would be able to do dou L by dou x2 hat. Let's move on to the next term, which is going to be dou L by dou sigma square. We again need this because the gradient needs to pass through this to be able to go to dou L by dou x, which is going to be an earlier term, and all the other gradients in the previous layers. Dou L by dou sigma square is given by dou L by dou x1 hat, which we already computed on the previous slide, into dou x1 hat by dou sigma square, which is the new term that we need to compute. Similarly, we need to do this for all the x terms. So you have dou L by dou x2 hat into dou x2 hat by dou sigma square, and it's written as a summation. The main term that we need to evaluate here is dou xi hat by dou sigma square, so which is found by the gradient of the form of xi hat itself. Let's go back a couple of slides and see what that is. So xi hat is given by this term here. So the gradient of dou xi hat by dou sigma just follows the gradient of this particular term, which can be written by xi minus mu into minus half into sigma square plus epsilon, which would have been the denominator, into minus 3 by 2. Similarly, we have dou L by dou mu, which is dou L by dou x1 hat into dou x1 hat by dou mu, plus dou L by dou x2 hat into dou x2 hat by dou mu, and also dou L by dou sigma square into dou sigma square by dou mu. So the first two terms get absorbed into a common summation, and the last term stays as it is. Dou xi hat by dou mu is given by this gradient here. This once again follows directly from the definition of xi hat to be xi minus mu by root sigma square plus epsilon. And the term here, dou sigma square by dou mu, gets written in terms of x's and mu's, because sigma square, once again by the same expression, can be rewritten in terms of all the x's and the corresponding mu. Just to repeat that, remember that if we go back to the algorithm, from the same boxed equation here, you could take sigma b square plus epsilon the other side and get xi hat as the denominator, and you would do this for x1 hat, x2 hat, and all of that. So dou mu by dou sigma square becomes a summation of all of these gradients, and that's what we get here. Each of this is one gradient with respect to one of those inputs, x1. Similarly, this would be the gradient with respect to x2, and so on and so forth. And that's how you get your dou L by dou mu. Finally, dou L by dou x1, that's the final gradient that you need to be able to compute to back propagate to earlier layers. That is going to be dou L by dou x1 hat into dou x1 hat by x1, plus dou L by dou sigma square into dou sigma square by x1, plus dou L by dou mu into dou mu by dou x1. So this one follows as it is, dou x1 hat by dou x1. By once again the definition of x1 hat, you will get it to be this term, dou sigma square by dou x1, once again by the expansion of sigma with respect to x1. Now you don't need to worry about the x2 term, so you'll have only one gradient term here. You get this. And finally, dou mu by dou x1 would simply be 1 by 2 here, by definition of x1, by definition of mu and how it's connected to x1. Similarly, you would get this for dou L by dou x1, and so on and so forth for all the dou L by dou xi's. That's how the backprop is done for batch normalization. A takeaway for you at this stage is, for any of these new parameters that you introduce in a neural network, a careful working out of chain rule for every term involved would take care of how you should be able to compute the gradients and backpropagate in that scenario. All that you need to ensure that you have only differentiable components in all your new additions to a neural network. With that, let's move on to convolutional neural networks, and this lecture is largely based on the excellent lectures of Mitesh Kapra from IIT Madras. Let's start with reviewing convolution. So we did do it in the first week of this course. We know now that convolution is a mathematical way of combining two signals to form a third signal. We also know that it's an extremely important technique in signal processing in general. Images are 2D signals, but convolution is also used for other kinds of signals such as speech or accelerometer data, time series data, so on and so forth. In case of 2D data, let's assume the simple case of grayscale images. Convolution operation between a filter W whose dimension is k cross k and an image X whose dimension is n1 cross n2 is expressed as y of yj, index u going from minus k to k, index v going from minus k to k, w uv, which is the filter, and x I minus u j minus k, which is the input image. We've already seen this as the definition of convolution. More generally, we can also write convolution in the form that you see here, where we are writing the indices going from the floor of minus k1 by 2 to k1 by 2 and minus k2 by 2 to k2 by 2. There's a particular reason we are talking about it, because if we write the equation of convolution this way, that's the only difference. Otherwise, the rest of it is more or less the same. Obviously, the indices of W change because of how we wrote the summation here, the indices in the summation here. All that we are saying in this definition is that we're going to center the filter on the pixel around which we are computing the convolution. We already did that earlier too, but we're just writing that formally here. So for different parts in the course, based on what we want to establish, we may write the definition of convolution slightly differently, but you can see that the heart of it, it's the same equation. You do have W indices and X indices defined this way, and you get the output at a particular pixel. We know from what we've seen so far that for the 1D case, when you do convolution, you slide a one-dimensional filter over a one-dimensional input. Similarly, in the 2D case, you slide a two-dimensional filter, as in images such as say Sobel edge filter and so on, over a two-dimensional input. Let's try to take this further. What would happen in a 3D case? Why do you need a 3D case? Isn't an image 2D? An image is 2D, but when you get to color images, you have 3 channels of images, which becomes a third dimension if you want to convolve with them together at one go. So let's try to understand how this convolution would look in the 3D case. Let's try to understand what a 3D filter would look like. Let's assume now that our input will be a color image which has 3 channels R, G and B, which makes the input now a volume. And what would a 3D filter look like? It would also be a volume. And we're going to refer to that as a volume going forward. So when you now slide the volume over your input volume and perform the convolution operation, you will be moving it across the input volume at different locations and getting one scalar output as the output of the convolution in the output image. So you can see that as you move the volume on different locations in the input volume, you get the output as pixels in the output image. We also call this output image as a feature map in convolutional neural networks. One assumption we make here is that the depth of this filter is the same as the depth of your input volume, and this is important. Why is it important? Because the depth of the filter is the same as the depth of the input volume. In effect, we are doing a 2D convolution on a 3D input. Why do we say that? We slide along the height and the width of the input, but we do not slide along the depth, because the depth of the filter is the same as the depth of your input volume. So your output of this operation will also be a 2D image. When you did 1D convolution with a 1D filter on a 1D signal, you got a 1D output. When you took a 2D filter on a 2D input, an image, you got a 2D output. Now we are taking a 3D filter on a 3D input, and our output now is not 3D but 2D. And why is that so? Because the depth of the filter is the same as the depth of the input. Then can't you get a volume? Can't you get a 3D as output here? You can, even with this operation you can, by defining multiple filters. If you define multiple such filter volumes, for each filter volume, you would get one such output or one such feature map. And by using multiple filters, you would get multiple such feature maps, which together form a volume. Let's now try to understand the dimensions. We know that even when we did convolution, we had some issues around the edges of the image where convolution cannot be performed, and we use techniques such as padding. Let's revisit some of those in the context of convolution, the way we see it for color images. Let's assume now that our input dimensions are W1 cross H1 cross D1 with height and depth, and the spatial extent f of each filter, the depth of each filter is the same as the depth of the input. So you have a spatial extent to be f cross f, and the depth is same as D1 because that's the depth of the input volume. Let's assume now that the output dimensions are W2 cross H2 cross D2. So we are now allowing the output to have some depth D2. If you used only one filter, this D2 will be 1. You can increase D2 by increasing the number of filters that you have. Let's try to work out a formula for W2 and H2 in this context. We will also talk about a quantity called stride, which decides how much you overlap successive convolutions on different parts of the image. And we will also talk about the number of filters in deciding the size of this output volume or output feature maps. Let's take it one by one. Let's first start with trying to compute the dimensions W2 and H2 of the output. So you have your standard convolution where you place your filter on a particular location in your input image. You convolve the filter with the input at that location, and you get one single scalar output at the centered pixel in your output, at the centered pixel location in your output, and you move this all along and keep getting different outputs in the different pixels as output in the output feature map. Let's try to now understand what happens if you place the kernel at the corners. So remember that if you place the kernel at the corners, you do not have inputs to compute the convolution of. So this is a problem with all these shaded regions here depending on the size of the filter. So this results in an output which is of smaller dimensions than the input. We've seen this earlier with convolution, but we are revisiting this to find out what would be the size of W2 and H2. As the size of the filter or the kernel increases, you can make out that even more pixels along the boundary are going to get affected. And for example, if you take a 5 by 5 kernel now, and as you slide this 5 by 5 kernel across, you're going to get an even smaller output because more border pixels are going to get affected because of you won't be able to convolve with those pixels that go outside the boundary. So you would have an entire region which is outside the boundary for which you will not be able to compute convolution. So your output in this case would be a 3 cross 3 matrix. We've seen these before. In general, we can say with this restricted setup that W2 will be W1 minus F plus 1 and H2 will be H1 minus F plus 1. So if your input was W1, in this case it's 7 cross 7, W1 and H1. F was 5 cross 5. So you have 7 minus 5 plus 1, which is 3, and the same for H2, and that makes your output a 3 cross 3 matrix. We saw earlier that if we want our output to be the same size as the input, we do what is known as padding. In the first week, we also talked about a few different ways of doing padding. The simplest way to do padding is to add zeros along multiple rows and columns outside the image so as to extend the original dimensions of the image. So that way you can convolve even the boundary pixels. Now you would have something like this. So your 7 by 7 becomes a 9 by 9, and now you can place your kernel even at the corners as you convolve your 3x3 filter on this image, and your output remains 7x7 as your input image. We now have W2 to be W1 minus F plus 2P plus 1, where 2P is the padding that you have done, and it's 2P because you have to pad along both ends, along the columns and both ends along the rows too. That's the reason you need 2P. We're going to further refine this formula. We are not done yet, and that's where we bring in the concept of a stride. When we convolve a filter over an input, we can also define the interval at which the filter is applied. When you move the filter from one location on the input to the next location, you can decide whether you would take it to the immediate next pixel or whether you want to jump 2 steps and go to 2 pixels later. And that decides what your stride is. So if you went to the immediate pixel, your stride is 1. That's the standard convolution. If you went 2 pixels further, your stride is 2, and that's where stride comes into the picture. So let's see an example. In this example, S is equal to 2 or stride is equal to 2. So you can see here that when you took your first 3x3 window and the next 3x3 window, you skipped one step in between and then went forward. And let's see these skips a bit more carefully. You can see those skips again. It's not only along the columns, it's also along the rows. You also skip pixels along the rows. The stride happens in both directions. And this is another way in which the size of your image output image gets reduced, and your new formula now with the stride included becomes W2 is equal to W1 minus F plus 2P, which is what we had earlier, which is now divided by S, the stride. Since the stride along the columns and the rows are the same, you use the same S. Technically speaking, the strides could be different between the rows and the columns, but in practice, it's generally retained as the same value. Are we done with finding the values of W and H2? Not yet done. There is one more detail left, and that detail is the depth of the output. As we already mentioned, the depth of the output comes from using multiple feature maps or multiple filters. Each filter gives us one 2D output, and k such filters will give us k such 2D outputs. As you can see now in the output region, we are saying now that the depth D2 is k. That's the number of filters you used. For each filter, you would completely convolve your filter volume with the input volume, get one 2D image. You take another filter. You could imagine taking a Sobel filter along a vertical Sobel filter and a horizontal Sobel detector. Those would be two different filters. So you run both of them and you will get two images as output. You just place them one after the other to form a volume. So your D2 or the depth of the output would be your number of filters, or k. Let's try to work out an exercise so you're clear about this. Let's consider this input to be 227 cross 227 cross 3. Let's assume that your filter size is 11 cross 11 cross 3. Let's assume that we're going to use 96 such filters. Okay. These numbers have a purpose which will probably be clear to you a couple of lectures down, but take these numbers for now as they are. You have 96 such filters. Let's assume a stride of 4 and a padding of 0, no padding. We already know that the formula is W2 is equal to W1 minus F plus 2P by S plus 1, and similarly for H2. Can we now find out what D2, W2 and H2 are? Let's start with the simplest one. What is D2? D2, as we said, is the number of filters, which means D2 is 96. Let's then go to H2. H2 was given by H1, 227, minus F, minus 11, plus 2P, which is 0, by stride by 4 plus 1, which is 55, and we get a similar value for W2. That's how you can get the output, the dimensions of the feature map. One important thing to keep in mind here is when you embed these kinds of operations in a neural network, unlike a feed-forward neural network where you would specify how many neurons you want in a first hidden layer, here the size of that next layer is automatically decided by the size of the filter and these choices that you make. In a feed-forward neural network, the number of weights gets decided by the number of hidden layers and the neurons in each hidden layer. And here it's the reverse. You decide the number of weights and the output map gets decided. We'll explain this in more detail as we go forward now.